say part B of first internal. So question 5. Briefly outline how to compute dissimilarities between students' feedback profile described by A. Nominal attributes example departments CSIT electronics selective chosen. So solution simple matching coefficient SMC. The coefficient measures the dissimilarity by calculating the ratio of mismatched attributes to the total number of attributes. It applies to nominal data where only equality matters. Match or mismatch. Dissimilarity is equals to number of mismatch divided by total number of attributes, which is P minus M divided by P, where P is the total number of attributes and M is the number of attributes where P profiles I and J have the same state. So the asymmetric binary attributes example attendant, workshop, CS no, CGPA, attendance percentage, etc. Solution Jacquard's distance. For asymmetric binary attributes, a 0-0 match absence of a characteristics in both profiles is often deemed uniformative and uninformative. The Jacquard distance focuses only on the instances where at least one profile has a positive value 1. Dissimilarity I is equal to R plus H divided by Q plus R plus S. So where Q is equal to number of attributes where both profiles are 1 positive match. R is equal to number of attributes where profiles I is 1 and J is 0, and S is equal to number of attributes where profile I is 0 and J is 1. See, numeric attributes example hours spent in mentoring, project reviews, attendance, assignments submitted, infrastructure usage count. Solution Euclidean and Manhattan distance. These are the standard distance metrics for numeric data typically applied after normalize the data. Example using z-score or min-max normalization to ensure all features contribute equally. Euclidean data distance L2 norm. Measure the straight line distance between 2 points in p-dimensional space. Dij is equals to under root of summation from k is equals to 1 to p into xik minus xjk square. So Manhattan distance L1 norm measure the distance traveled along the axis. City block distance Dij is equals to summation of k is equals to 1 to v mod of xik minus xjk. So term frequency vectors keyword in open text feedback. Solution cosine distance. Term frequency vector like TF1 IDF are high dimensional and sparse. Cosine similarity measure the angle between the two vectors, which indicates the proportional similarity irrespective of the vector magnitude document length. Similarity AB is equals to cos theta is equals to A dot B divided by magnitude of A dot magnitude of B. The dissimilarity is then defined as dA dot B is equal to 1 minus similarity A B and B. Question 6 distance calculation. Suppose two students of faculty interaction profiles are represented as tuple P is equals to 22, 1, 42, 10 and Q is equals to 20, 0, 36, 8. Compute the following distance. Profile component. So here is the attribute and here is x1, x2, x3, x4 and here is the difference of them. So A Euclidean distance L2 norm. So D here is the formula of Euclidean distance. So we are putting values x I k. So 2 pi square plus 1 square plus 6 square plus 2 square. So dpq is equal to 4 plus 1 plus 36 plus 4 divided under root 45 is equal to 6.708. So Manhattan distance. So here is the formula for Manhattan distance and we are putting values in it. So mod of 2 plus 1 plus 6 plus 2 is equals to 11. So Minkowski distance with h is equals to 3 is the general Minkowski formula is dpq is equals to summation of k is equals to 1 to a mod of xk minus yk to the power h to the power 1 divided by h. So we are putting the value in this formula, which is cube root of 2 to the power cube plus 1 cube plus 6 to the power cube plus 2 to the power cube is equals to cube root of 8 plus 1 plus 2 and 6 plus 8 is equals to, which is equals to 6.154. So supremum distance. The supremum distance is the maximum absolute difference between the components. dpq is equal to maximum of 2162, which is 6. So question 7 median approximation. The median score is often a key holistic indicator of faculty or infrastructure performance when dealing with massive student feedback datasets. Proposed methods for median approximation analyze this complexity and suggest a heuristic to balance accuracy versus efficiency. Context and complexity. Finding the exact median in a massive dataset requires sorting the entire stream, which is highly inefficient in terms of computation time. Big of n log n and memory big of n for streaming distributed environments. Therefore, approximation is necessary. Methods for median approximation. First is sampling heuristic description. Calculate the exact median on a carefully selected random subset sample of the data, say 1% of the total. In trade-off, offer high efficiency computation time scales with the sample size big of n log n where n is less than n. Accuracy is excellent, provides the sample is truly random and representative of the population distribution. Second is binning and histogram based approximation description. Divide the data range into fixed width bins and count the frequency in each bin. The median is approximated by interpolating within the bin that contain the 50th percentile count. Trade-off offers a high efficiency because in single pass accuracy depends on the number and width of the bins. Fewer bins lead to faster computation but lower accuracy. The third is quantile sketching algorithm. Description. Algorithms like Greenwald can maintain a compact summary sketch of the data stream. The guarantee an approximate median. The return value is within a small error bound of the true median. The trade-off offer the best accuracy versus efficiency balance in streaming scenarios requiring big of a 1 log n memory and big of log n or big of 1 update time per data point. This provides provable error bounds. Question 8. Similarity ranking and normalization. Consider student faculty similarity analysis. A query student profile is X is equal to 1.4, 1.6. The database has the following student profiles: student 1, student 2, student 3, and student 2, the student 5. So it rank the existing student based on their similarity to using Euclidean distance principle. Lower Euclidean distance indicates higher similarity. So student S1 using Euclidean distance formula. So distance is equal to 0.145. So most similar. For S2 distance is equal to 0.42 third. For S3 distance is equal to 0.632 5 least similar. For S4 distance is equal to 0.2242 and for S5 distance is equals to 4. Final ranking most similar on least similar. So S1 is greater than S4, S4 is greater than S2, S2 is greater than S5, and S5 is greater than S3. So at B, normalize the student profiles to unit length. L2 norm principle. Normalization ensures that similarity is based on the direction of the vector, the ratio of feature values rather than the magnitude overall score volume. So normalized S is equal to S divided by magnitude of S, where a magnitude of S is equal to x square plus y square. So here is the student data and we calculated magnitude using this formula, which is 2.267 for S1, 2.550 for S2, and all magnitudes are there for all the students, and normalized x is equals to this 0.662, 0.667, and normalized y 0.750, 0.7452, 0.555.